equations, if an equations that we use to represent the problem to be solved, as I mentioned just now, and it is needed in order for us to solve the problem. Okay? Okay. Now, let me see. Okay. So governing differential equations is derived by taking one small part out of the elastic body that we are trying to solve. So governing differential equations, if I have this and depending on the case, there might be body force. And body force in 1D problem is normally given in terms of force per unit length, okay? Force per unit length, because we already specialized 1D problem. But if it is a general overall 3D problem, body force can be force per unit volume. But in 1D problem, this body force is force per unit length. And let's say it is given as, this is given as W, which is a function of X. This is body force. Okay. Then we will have the coordinate representing the problem and the non-zero displacement U. So this is X is equal to 0, and this is X is equal to L, and this whole thing, the length is L. And to derive the governing differential equations that we go through is d dx, AE, du dx, plus the body force equals 0. Okay? If I represent body force using W, this is the equation that you need to use to solve a 1D bar problems using theory of elasticity. And how do we get this is we make use of the three basic relations. We take one small part of this out here. We take one small part of this, which is a slice out at the distance x, and this is dx. So we take that small part out, okay, and look at all the forces acting over there. So let's say the cross-sectional area here is A. And the cross-sectional area here is A, okay, and we have this body force, which is force per unit length. Okay, there's a Wx at that particular point, so I just put it as W. And other than that, you have the stress, sigma x. And when you come to this side also, we have a sigma x plus delta sigma x. So here, take note that we assume that this has intention. Our assumption is our stresses, we assume intention. Okay? This is the positive x surface, so it follows the positive x. This is negative x surface, so the positive direction is follow the negative x axis direction. So this is the stresses. Okay? So by considering the equilibrium, we have sigma x plus delta sigma x, and this is, we consider delta x first, later we can try to take it to the limit of dx, okay? We consider delta x here. Later, we take it to the limit of dx, so we can get the differential equation. So sigma x plus delta sigma x multiplied with A. So equilibrium must be forces. Okay? Equilibrium must be forces. So we must take note of the forces on this side. So plus, this is W acting over this small distance. So over this small distance, consider it as constant. So we have W delta x. Then minus, on the other side, minus sigma x multiplied with A, and this is 0. Okay. So if we simplify this, so if we get A, this plus W delta x equal to 0. Okay. If we divide this, okay, if we divide this with delta x, okay, and take delta x to the limit, yeah, we divide this with delta x, and then delta x go to the limit, which is, then we get so we get first this is purely equilibrium of forces. This is purely equilibrium of forces, where we also take into consideration the sectional shape, but there's nothing, material properties, stress strain relations, I think is nothing inside there yet. So we get this. Okay. So next if we, let me write here. So next, if we try to take the other basic relations now, stress strain relations. Stress strain relations, then we have sigma x is equal to E epsilon x. So we can substitute here E epsilon x. And then further, we have the strain displacement relations. Plane displacement relations, then you have epsilon x is equal to du dx. Okay. Okay, so okay. Okay. So what do we get next? So if you have this A, there was sigma x plus sigma x plus A, sigma x minus, so A delta sigma x delta x, so it's dx. X. Sigma x and dx. Let's see, we get A. Okay. Second class, let me